Today we're going to finish section 3.4, which is multiplication of whole numbers. And we are jumping right back in at the point where we're going to talk about one type of multiplication that pops up when we're multiplying, and that's dealing with exponents. So for starters, if you have a raised to the power of n, which means a multiplied by itself n times, then we call the letter a the base. We call the letter n an exponent. And in what we're working with, we're going to use the letter or the number n to be natural numbers. There's no reason that it's confined to be that way, but we're working with natural and whole numbers right now, so that's what we're focusing on, okay? When you get into other sections and chapters of this book, we'll expand our definition. There are four basic properties that show up right now. When you take proportional and statistical reasoning, we have an additional two that show up in that section in chapter, 6 or 7, something like that. But for now, 4 is enough. So let's see if you guys remember. And then what I want to show you is actually why these theorems are true. So does anybody remember what happens when you have a to the m times a to the n?
You get a to the m plus n.
All right, so you add exponents, and that is correct. So good remembrance. We add the exponents together. Number 2, if when we're multiplying bases, we add the exponents, what do you think happens when we're dividing them? You subtract. So this is a to the m minus n. How is 3 different than 1?
It's multiplying both a and m.
No, it looks like it because of the parentheses, so that's definitely a misconception that's common, but that's not what's going on. There's something different.
Oh, it's power. It's whatever a to the m is, it's going to.
Yeah.
With the a to the m.
Yeah. So on part 3, what you're seeing is a power on the outside raising what's inside, which already has. So it's like an exponent to an exponent, right? An exponent raised to another exponent. Whereas on number 1, you're seeing 2 bases that each have exponents being multiplied. So on 3, when you have an exponent raised to the exponent, you actually end up multiplying the exponents together. And again, I'll justify that in a moment, but that is the truth. 4 is more like what you were describing earlier, Danielle. So on number 4, you have what sort of looks like a distribution property. You have AB raised to the power m, and again, I'll show you why, but it's basically because of commutativity properties that this is a to the m, b to the m. Okay, so I'm going to justify in a way that I just told you a minute ago does not actually prove anything's true. I'm going to do this. This is like proof by example. Did you ever have anybody in high school who tell you this is proof by example? I had professors and teachers along the way who would say things like that. What that means is that I'm not really proving it, but I'm justifying it in such a way that hopefully you believe it. Okay? It makes it believable. And it is a true statement. I'm just not interested in making a full-out proof. I'm interested in justifying it for you. So we said the first one should be the addition of exponents, right? This is what it should be. And I want to show you here over to the side, you can write this justification down why it works. So the example that I want to do is going to have a to the third and a squared. Okay, so what does a to the third mean? A times a times a. Okay, what does a squared mean? A times a. All right, so now how many a's do I have? 5. So if I've got a multiplied by itself 5 times, that's a to the 5th. And if you take a look at the exponents, 3 and 2 became 5. What operation does that? Addition. It's an addition operation. All right, the second one we said should be subtraction of exponents like this. So I'm going to do one that is a to the 4th over a to the 1st. And I'm going to write the first down just so that we can see it there. So a to the 4th is a times a times a times a 4 times, right? And a to the 1st is a by itself. So fraction. You guys have worked with fractions before, not in my class, but you have in other math classes before you got to me. And one of the facts that you know about fractions is that if it has a factor on the top and the bottom that match, that you can reduce them. And so when I do that, I'm left with a times a times a, which is what? A to the third. And just like the last time, how do you get from 4 and 1 to 3? You subtract. Subtract. Number 3, we said that we were going to multiply the exponents together. And I'm going to choose a similar example to what I did on number 1, a to the third squared. So I've still got that same 3 and the 2 showing up. Okay, so the a cubed part means that I have a times a times a, right? And then the squared on the outside means that whatever is inside that parenthesis is there twice. So I have a times a, like that. Okay, how many a's is that? 6. There are 6 a's there. And how do I get to 6 from a, 3 and a 2? 2 times 3, I multiply. Indeed, I do. And then the last one we said is somewhat similar to a distribution property, a to the m, b to the m. And we're going to do as an example, ab cubed. So just like on the last problem directly above this on my screen, I said that whatever's in the parentheses got repeated twice. Well, this one's cubed, so whatever's in the parentheses, namely AB, gets repeated 3 times because it's cubed. That's really what it means. But one of the things that we've talked about already in this section that you watched on the video is the fact that multiplication is commutative, right? I can switch the orders of things around and regroup to nice factors and things like that to multiply it out and all that good stuff. So I can actually put all my A's together, and then I can put all my B's together, and that would be acceptable and right because it's commutative and associative properties playing out. And then sure enough, I get A cubed, B cubed as a result. And you can see comparing that back, again, it looks like the cubed has been distributed to the A and distributed to the B. Okay, so every now and then I go through this, and then when I get to homeworks or tests or something like that, students are trying to do all the stuff that I just did on the right-hand side with these examples on all their problems, and that's not my goal. My goal in doing that is so that at some point in the future, if some, rascally little kid in your class says, "But why, Miss Witt? I don't understand," you can be like, okay, well, my teacher told me this somewhere along the way, and I've seen it before, and you can go back and look at what you had, or you can pull it up online or whatever, so that it's not like you're, deer in the headlights going, I don't know why, because my teacher told me it was. Like, that's not a good answer. But you can say to them, let me get back to you, little Johnny. Apparently Johnny's the name that I use for these kinds of things. My husband told me that the other day. Why is Johnny always the bad kid? And I'm like, well, he's not. It's just the name I'm using. Little Johnny, I can come back to you and I can talk to you about it tomorrow, and you can have a chance to go and find out that information. So our goal really is to use these 4 properties as is. So if I need to have an exponent over an exponent, I know I get to subtract. If I need to do, an exponent where it's distributed, I just distribute it. I'm not trying to get you to prove it or to show it every single time. That's not the goal. Okay? Everybody good with that? All right. So let's take a couple of examples, and we'll be able to apply them. So example number 4, part A, says I have 5 to the 10th times 5 squared times 5 to the 4th. So what would I do to combine or simplify this expression? The goal is not to multiply this whole thing out. It is to have it written as a base to an exponent when I'm done, okay? So how would I do that on this problem?
5 to the 10 plus 2 plus 4.
Right. So that's property number 1, right? Property number 1 says if the bases match, which they do, they're all base 5, I can simply add the exponents together. 10 plus 2 plus 4 is what? 16. So this is 5 to the 16th. Applied the properties that we have, we're done. B is slightly different. What's going on B?
Bases are different.
The bases are different. I have a 6 and I have a 2 and I have a 3. There's two different ways that you could do the problem, both equally correct from different perspectives. Does anybody have any idea what they might try to do if they saw this problem?
Add the base and then add
So you would like to add 6 plus 2 plus 3?
the.
Yeah.
That,
Nice try.
that would be something that someone would try to do.
It is something that someone would try to do, yeah. We can't add the bases because all the properties that I just showed you are contingent, except for number 4, because it was about distribution, did a little bit differently. But all those properties, 1, 2, and 3, were all contingent upon the bases matching, and these bases don't match. Do you have an idea, Annika?
So we can use number 4 since the exponents match for 2 and 3. Pretend 2 and 3 are A and B.
Okay, so I agree with you. That is one of the two ways to do the problem for sure. I can recognize that the 2 and the 3 here have the same power. Do you guys see that they have the same exponent on them? And I can use property number 4 kind of in reverse. Properties work both directions. We tend to start here and we go here, right? But there's absolutely nothing that says we can't start on the right and move to the left. And we can. We absolutely can because it's an equality. That's what equalities mean. It means that it equals both sides, right? I can move left to right just like I can move right to left. So what I could do is I could write the 2 and 3 in parentheses with the 3 on the outside. That's 6 to the 4th still at the beginning. Sorry about that. And then what do you notice happens when you multiply 2 times 3? You get a 6. So now you have 6 to the 4th and you have 6 cubed. Do the bases now match? Indeed. So what can I do next?
Add the exponents.
Yeah, I can add the exponents so I get 6 to the 7th. So this is one way of doing this problem. This is probably my favorite way of doing this problem. I think it's cleaner at the end. I do want to show you one other option just in case you were checking this answer in the back of the book and you're like, it does not say 6 to the 7th, so my teacher did something wrong. I want to show you another option just in case, okay? So let me show you what else you could do. Instead of combining the 2 and the 3, what you could do is you could take the 6 and you could break it apart. So at the beginning, that first 6 is actually 2 times 3 as well. Okay, is that good with everybody? So instead of combining the 2 and the 3 at the end, I break apart the 6 at the beginning. If I do that, I can distribute, again using property number 4, the 4 across this. So I have 2 to the 4th, 3 to the 4th, and then I have 2 cubed, 3 cubed. Is everybody good so far? Well, you know, these go in pairs, right? Whoops, I meant to get the highlighter. This one and this one are both base 2s. Agreed? So I can use property number 1 and write them as 2 to the 4 plus 3. And then these are both 3 with powers. So again, I can use property number 1 and I can rewrite 3 to the 4th plus 3, like that. So 4 plus 3, of course, is 7. So an equal answer would be 2 to the 7th, 3 to the 7th. I'm not suggesting then that you combine them back into 6 to the 7th, although you certainly could. But this would be another version of the exact same answer, but in a different form, right? It's a different version of it. So both of those are possible versions. This one has the benefit, if you sort of think about like merit, like that problem asked that you had, Danielle, like what's the merit of doing something, right? This one has the merit or the benefit or the pro, if you will, about the fact that it's very condensed and clean, right? 1 base, 1 exponent. That's very nice. This one has the benefit when we get into chapter 4 of being in prime factorization. The base are primes, right? 2 and 3 are prime numbers. 6 is not a prime number. So it kind of depends on what you're wanting to do with the problem next, if we're continuing, as to which one's sort of better. All right, enough with exponents. You ready to learn some interesting algorithms for multiplication? All right. So I have a daughter who is very bright. She's very capable, especially mathematics. Math just clicks for her. Some of you are like, yeah, you relate to that. And some of you are like, what's that all about? So, but multiplication was one of those areas that was not easy for her. She struggled a little bit with it. And so when she learned the standard algorithm for multiplication that you know and love, and you're like, why would you do it any other way? It didn't make any sense to her. And she's very capable in mathematics. And so it was a very frustrating experience for her. And so don't always think, too, that it's the math kids who are going to get the standard things that we do and the non-math kids that need the other stuff. It doesn't work out that way all the time. So I know that you know the standard algorithm, and so we'll write that one down first, just on the left-hand side of my screen right now, and then I'll show you how that looks if you do it in expanded form. So for the standard algorithm, here's 48 times 32. And we're going to talk through it. So where do you start? When you think, I'm going to multiply 48 times 32, and I don't have a calculator with me, which would be highly unlikely at this point because you all have phones in your pocket. But pretend for a moment that you're back in 3rd grade and they don't let you do that, or 4th grade or whatever. What would you do first? Right, so we start with the right-hand column, all right? So in spite of the fact that we read from left to right, we're going to do math from right to left. Already we got sort of a difference there, right? All right, so what is 8 times 2? 16. And what do I do with my 16? Okay, I write a 1 up here, and then I put a 6 underneath here, okay? So that's kind of like addition, right? You know, in addition, I move the tens digit over and so forth, so that has sort of a nice feel to it. What do I do next?
2 times 4.
Oh, so I go along a diagonal now, right? I'm no longer going vertically. I've changed to diagonal notation. That's exciting. So 4 times 2 is 8. And then after I do the 8, what do I do?
Add the 1.
Wait a minute. I thought we were multiplying.
Well,
You still have to add the carried over.
I do. So in the middle of multiplying, I change my operation and I'm going to add.
yeah.
Yeah, I am, right?
Yeah.
Fabulous. So in the middle of multiplying, now I'm adding. It's exciting. Then what do I do?
Put a 0.
A 0 just shows up from nowhere.
Because you have to add a place value.
I do, but it just showed up, right? Like, I didn't have to do that with addition. All of a sudden now, in the middle of this particular problem, I've inserted a 0. I hear people say things like this, invisible. It's not invisible. I see it. But it sort of showed up from nowhere. It's like a magic 0. Right, like the magic E on the end of reading. Y'all know what I'm talking about, right?
Yeah.
Used to call it silent E's when I was a kid. They call them magic E's now. Magic E's, yeah. Okay, there's a 0 that shows up. Then what do I do?
3 times 8.
I do this other weird, like, diagonal thing going on. 3 times 8, and 3 times 8 is 24. So I put a 4 down, and then what do I do?
Carry it over.
I carry a 2, but there was already 1 there.
You mark out.
Mark out
I just ignore it. I multiply, right? Just mark it out. Now I've got a 2. That's good. And then what do I do?
3 times 4.
3 times 4, which is 12. And then again, in the middle of my multiplication, I add. That's exciting. There I've got a 14, right? And then when it's all said and done, my addition problem at the end,
You add me
I add again, right? So I've got a 6, a 3, I carry my 1, so that's 5. I've got 1536. I hope that you can kind of get the feel of why this is a little bit challenging for students. Because there's a lot going on in that problem. I had a 0 show up. I had addition occurring in the middle of multiplication. The multiplication of carried values changed the value that I had from before. There's a lot going on in the middle of a standard algorithm for a multiplication. A lot. So let's look at what happens from an expanded standard algorithm so you can see where the pieces are actually showing up and why this actually maybe works. So here's what I'm going to do. I'm going to write down 40 plus 8 and 30 plus 2. And for your kiddos who are more visual, hold tight. Partial products, which is the next algorithm, is even better for a visual learner. Okay, so the idea here is that I need to multiply the values by one another. So you can do this in any order because of the way I'm doing that. I'm just going to start from left to right, just like we read. So I have the 40 times 30. Well, what's 40 times 30? I have, close, 1,200. Okay, right? Double the zeros. And again, I can do it again in any order. So if you want to do the 8 times 2 next, you can. I'm going to actually do my 2 diagonals next. So 40 times 2 would give me 80. And 30 times 8 would give me 240. And then the last one that I haven't done so far is the 8 times 2, which gives me 16. So one of the beautiful things about what I just did is that I did all the multiplication in the same step. There was no mixing and addition in the middle of my multiplication, right? That's really helpful for students to isolate what's going on. The other thing that it does is it really flushes out the place values. I didn't do 4 times 2. I did 40 times 2 because that's what that 4 really means. And that's why that 0 showed up. Emma was trying to tell me, and I was trying to be kind of a little bit snarky with her when she was saying it back there. But it's a place value. There's a holder for it. And you're right. There totally is. Absolutely. And the reason it's showing up is because the multiplication that we're doing here is actually 30, not 3. It's not 3 times 8. It's 30 times 8. That's why there's a 0. Okay? So over here, all of that's just cleanly flushed out. It's all right there. And then you're adding all the pieces that are left over. And if you wish to write them vertically, of course you can. So I've got 1,200. I'll just do them in place value of decreasing order. 240, 80, and what did I have, 16? 16. And I know that we can write this down as 1536, and there's a little bit of regrouping in the middle of that. I get that. But what it does is it isolates the values in different orders. And it also does, in fact, make it able to be done from left to right if you wish. Okay, is there more writing? Yeah, there's more writing. Is it efficient? It's not especially efficient, but it's very obvious where all the values are coming from. Now, if you're even a little bit more visual, the next one, partial products, is even better. So what we're going to do is we're going to actually draw a grid, like a square, and it needs to have 4 compartments in it, okay? And you're going to write the values that you have broken apart, just like I did on the last problem with the expanded algorithm, 48. So this is 40 and 8, just like this. And then I have 30 and 2 along the right side, okay? It doesn't really matter if it's on the right-hand side or the left-hand side. I put it on the right-hand side because in a minute, when we do the lattice algorithm, it really does matter, and it has to be on the right-hand side. So I'm just always put it on the right-hand side so I don't have to remember which one's which. And each of the boxes actually allows me to do the multiplication and put the number inside the box. And I'll draw you one more visual of this in a moment. All these numbers we've seen before. I have 1,200, I have 240, I have 80, and I have 16. So each of the numbers is simply, so like right here, it's 40 times 30, so it's 1,200 in that first box. On this one, I have 8 times 30, so I've got 240 in the box. So the column and the row match up and they multiply. And then just like the other one, you add them when you're done. So you have 1,200, 240, 80, 16, and you get 1,536. But let me actually show you what this is beckoning to. It's beckoning to one of the models that you saw already earlier in this section called the area model. So let me draw it in the dimensions a little bit better. What you really have is something like this going on. This is 40 wide, and this is 8 wide. So this box right here, oh wait, let me get the other pieces in here. This is 30 deep or long, and this is 2 long. So what you really see happening here is you can see why this is 1,200, right? Compared to the 16 that's showing up down here. It's area, it's space that's involved. So this partial products is actually an abbreviation of the full area picture that's happening when you think of multiplication as area. Partial products is my favorite algorithm for multiplication, without question. And still, when I showed my daughter partial products, she still wasn't getting it. So let me show you the one that she did get. Are you ready? The one that she did get was the lattice algorithm. And she doesn't do lattice algorithm. She's in 10th grade. She didn't do this today. She can do the standard algorithm. It's no big deal. And of course, in 10th grade, she's using a calculator anyway, and it's not a problem, right? But this is the one that made sense to her. So go ahead and draw, again, that same box that you did before, divvied up into 4s. And the reason that they're in 4s is because we're working with 2-digit numbers. If I had 3-digit numbers, I'd have a box with 9 little boxes inside. If I had a 3-digit by a 2-digit, I'd have 6 little boxes inside. It's just the size of the values. You're going to write the digits on there, but they aren't place values. They're actually the single digits. So this is a 4 and an 8 and a 3 and a 2. Okay, so they're individual values. And we've seen lattice before, and what you saw before, in fact, is that you split up your box into diagonals. just like partial products, what you're going to do is you're going to do the row and the column that they're on, and you're going to write the product in it. So the first box in the top left-hand corner is 4 times 3, which is 12. So the 1 in the top corner, the 2 on the bottom corner. The 8 times 3 is 24. 4 times 2 is 8, so it's just a 1-digit number just in the bottom corner. And then 8 times 2 is 16. So I have a 1 and a 6. And this is where it's much like what we did when we did the lattice algorithm for addition, is that you extend the diagonals and you're going to add along the diagonals. And it really does matter. You have to start in the bottom right-hand corner. So that's a 6, right? You're just adding numbers that are inside the box, not the outside of the box. My next diagonal here, I have an 8 and a 1 and a 4. That's 13. So I do have to write down the 3, and I do have to carry a 1. So there is carrying involved. It doesn't eliminate the need for that. I have 2, 2, and 1, which is a 5. And then my uppermost diagonal is a 1. So there's the 1536. For whatever reason, this is the one that clicked with my daughter. Yes, Emma?
So I actually hated this method when I learned it.
Did you?
Yeah, but the blank spot, is it okay if I put a 0 in
Sure.
the brain for it to work?
Yeah, absolutely. Yeah, so she's asking if she can put a 0 right here. Yep, if that helps, go for it.
In elementary, they tried to teach us this, and this was, I hated this more than anything.
Yeah.
Because I was so confused with why there were boxes and
Yeah.
why we had to like have it go diagonal instead of across.
Yeah, and the diagonals are splitting at place values, what's happening. I mean, like, that's what's really going on behind the scenes. But I think that what you guys are doing is you're telling me that there's methods that work for you and there's methods that don't. What I want you to take away, I've got one more to show you, but I won't do it today. Oh, no, I don't. This is actually ending a nice place. What I want you to take away from these methods is the fact that just because it didn't make sense to you doesn't mean it won't make sense to some child in your class that's struggling. And just because they're really smart in math, right, doesn't necessarily mean the standard algorithm is going to be the one that beckons to them either, just like it wasn't in this case for my daughter. All right, there are different methods. You don't know what your curriculum is going to require out of you or what's going to work for your kids. So having more options at your disposal can only help you as a teacher. All right, we will pick up tomorrow or Wednesday on the next part of this lesson.